University of Science and Technology of China, and Tsinghua University. The title is the Drum Periodicity Theorem and Periodic Drum Conjecture. Let's welcome.
Thanks for the introduction. So today I will talk about Today talk about the periodicity. And its relation with some Grond-Descartes conjecture. So start with a family of elliptic curves, and we know so we have this holomorphic one form, and then we have this defined as normalized period. Okay, so it's normalized period. So it encodes very deep information of this elliptic curve, but today's this number is very difficult to compute. But good news is that when you deform T, actually these periods, the periods satisfy a linear ODE. This is an R2 linear ODE. Understand this ODE will help us to understand the periods. But this is actually the full phenomenon in Hodge theory. So actually, all period integrals attach families of complex algebraic varieties satisfy certain linear ODE, and we call the whole collections of this ODE by Picard-Fuchs. Okay, so and today's talk actually stems from one very basic question. So is any linear ODE Picard-Fuchs? Okay, and certainly you will guess. And you don't need to guess actually. The answer is no. So we rewrite the ODE, linear ODE is a holomorphic coefficient. So actually, so we rewrite this as this trivial bundle. So here I already assume that this is actually a fact that this must have a singularity. There's no smooth family over P1, even over C, because the fundamental group of C is trivial. So the bundle must trivial. You can trivialize, but you have the connection. And so connection is the nature of holomorphic one form. This actually is just a reformulation of this the previous slide. This linear ODE with holomorphic coefficient. So here comes a big result of by Delaney. This connection, if it is Picard-Fuchs, must have only have a singularity with so-called regular singularity. So if you express this connection with a holomorphic basis, then must at the most the order of pole is less than is equal to 1 if you have a pole after all. And then extend this connection to an logarithmic connection on the P1, then that's by a Gaga principle, you'll get the information that the entries of connection actually is just one form. It's not holomorphic one form. It's algebraic one form, rational one form. And furthermore, by the result of Steenbrink in his thesis, he showed that this residue of this connection, extended connection, actually have a rational structure. So-called the residues must be rational numbers. So this corresponds to the geometric fact that the local monogeomy of a geometric local system are actually quasi-unipotent. That means the eigenvalues of this local monogeomy matrix is a root of unity. So this actually exclude this cut down the parameter. I mean, from the moduli space of the linear ODE to a very this is very narrow range. You have this rationality here, and you have this the constraint of the pole order here. And then the central problem becomes how to characterize Picard-Fuchs equation among all linear ODEs. And we should know that this question is actually Asian questions in different disguise. It's already noted by Euler. I learned this fact actually from the exploratory article by Bert Totaro. He wrote an exploratory article about Euler and algebraic geometry. And this article contains two topics. One is about these questions. The second is about this finite generation of the canonic ring. So this part is in the Bearcast expertise. Here we have several important conjectures, in the literature. So the first, I list three. This actually is the most representative one from different perspective. So first one is a Simpson standard conjecture. So he have assumption, but I believe we can actually relax this assumption to a finite general field of Q. So suppose U is defined Q bar. That means the puncture, P1, the U is just complement of several punctures defined of Q bar. And you have an algebraic connections over this U with regular singularity. Since we know that if you just pick up Fuchs, it must have only regular singularity. So we assume it. And suppose the complex local system attached to it by the classical Riemann-Hilbert is defined of a Q bar. So this is a bi-Q bar structure. So then the conjecture becomes, they say this must be Picard-Fuchs. Okay? Yeah. So this is you can say this is a Beatty and this is Drum. So it's a Beatty to Drum, or Drum to Beatty. So if in these two sides you have both have a Q bar structure, that is a conjecture that is created. So it must be algebraic. It must be Picard-Fuchs. The second one is a so-called Pombieri-Dvorak conjecture. So it involves some periodic analysis. So the terminology is a G connection. So G connection is a linear ODE satisfied by a G function. But which I will not explain here. It's pretty long, and it's a power series which defines the coefficients in the number field, and the radius, the periodic radius have a control, including the all conjugation. But this is a notion introduced by Ziegel in his Davanting approximation. So the conjecture, this is also a famous conjecture in the theory of the study of G functions. Every G connection is Picard-Fuchs. Certainly, they prove that if it is Picard-Fuchs, this is satisfied. So it's G connection, but this is a converse direction.
Is G a finite Lie group?
No, G is a name. I don't know how it comes. Actually, there are G function and E functions, so nothing to do with Lie group. Okay. So actually, this is important to relate these two conjectures. This actually kind of compatibility or comparison of Riemann-Hilbert at infinity, at the Archimedean place, and the periodic Riemann-Hilbert. Today's focus is on the so-called the Golden-Descartes-André nilpotency conjecture. So they conject that globally nilpotent connection is Picard-Fuchs. Okay. Before I explain this notion, so let me point out that this is really a purely algebraic conjectural characterization. Okay. And the key underlying this notion is about this P curvature. So it's a new notion which you will not see at infinity, at the Archimedean place. You can only see this at the phi prime. So let me explain. So now we suppose we have a character P field, and U is a curve, smooth curve over U of K, and then this tangent bundle of the curve of your space equipped with a two structure. One structure is a character free. This is a Lie structure. The second structure is so-called P power map. So the P power map is it means just you have a derivation, you just compose it consecutively p times. Then in character p, it is still a derivation. So this is power p map. And this triple is termed by Jacobson in the 40s, last century, as a restricted algebra. Actually, this is starting point, so-called the inseparable Galois theory. So his aims to find a replacement, a correct analog for inseparable Galois extension. I mean, to extend the usual Galois theory. And for an algebraic connection, I mean, we write this in this form. I mean, looks like it's a quasi-representation. So you have this restricted algebra, and the right-hand side you have also the structure of as a restricted algebra. So you have this bracket, you have this power p map, and the p curvature measures as a usual curvature. I mean, to measure the difference of these two structures. So now the curvature vanishes just because of dimension reason. U is a curve, so it's 0. But the p curvature, so measure this difference of two structures. Okay, it's not necessary 0. So now I just introduce a spread out, just because I want to pass from our character 0 story to the character p. So we need to spread out our model. I mean, to spread out our object over C to an arithmetic model, to spread along the direction of spec Z. So A will be a function is the subalgebra of C, and you will find some good model, so that if you tensor back this embedding, so I mean this is C, A is a subalgebra of C, so it will give you back our starting algebraic connection. This is possible, so because all things here is a finite generated. So you have this this Northern property to guarantee you can do this spread out. Once you get a spread out, and then you can mod p. So here's a famous Grothendieck p-curve conjecture. So suppose you have an algebraic connection over a complex curve, and if their sum spread out such that for all geometric point in this your base, so I say it's a spread out over S. S is a finite type of a spec Z. And the reduction has a vanishing p curvature. Okay, so that means in this literally, so all curvatures you can imagine vanishes. Then the conjecture asserts that the connection must be algebraically solvable. It means that it admits full rank algebraic solutions. Here, algebraic means just involve only take a radical. I mean, take the radical of your base function. That means it also equivalent to say that this connection is finite Étale trivializable. Okay, I will take the Étale base change of U, and you pull back connection on the covering. It will become just D. Okay, so the bundle is not interesting, right? The bundle is trivial bundle. The only thing is really about the connection. So we call such a property is a globally vanishing. I mean, all curvature p curvature vanish, and actually the property is independent of choice of your spread out. If one spread out have this property, here actually if you want remove form it this way should depends. Is you need to removing a proper closed subset of your S. But if you put in this into this is the original statement of the p curvature. But you can exam spread out, and here you exist some closed proper closed subset of Z, Z of S, such that S away from Z this satisfies. Okay, then if formulated in that way, this is really independent of choice of spread out. And this actually is a local to global principle. Actually, vanish of p curvature means that over P, you can solve it completely. It means the full rank algebraic solutions. This is so-called Cartesian descent theorem, and this theorem will come back in the our later. And the conjecture, so the status of the conjecture is that this is proven. First, actually, this is by cuts in the, if this is a Picard-Fuchs. And then it is by Chardovsky brothers in some unreadable paper. And then this replaced by algebraic geometer by André and Bost. This different proof. The different proof. But André relies on this work, and Bost is a use foliations. And also some property at infinity, so-called Liouville property. Anyway, so he used a Alekirov geometry. Use some slope to bound this to give some inequality. And so this is status. But to summarize, we should know that this conjecture is still largely unknown. Okay. So now let me take a smooth project curve, C, and we can take KC to be the function field, and we reformulate the Picard-Fuchs property as follows. So a C connection, over the function field, see, is said to be motivic if it is isomorphic to a subspace of the Gauss-Menin system over some, this is over some undetermined U. Here's the point is we only care about the subspace. Here the subspace means really it's not just it's a sub-object of this pair. Okay, so it means there's a subspace of the KC finite dimensional case vector space HDR times the KC, and which is invariant on this connection. Okay, so so this we call this motivic. So it's not necessary to be Picard-Fuchs anymore. It's it's just a subquotient of the Picard-Fuchs. And it's actually this create some additional structures and additional difficulty. So for example, Katz cannot show that he can show that the P curvature for whole Picard-Fuchs, but he cannot show arbitrary this motivic. Yeah. If it is this space is created by cut down by some finite group action on the family, then this is okay. But it's an abstract subspace. This is still unknown. Okay, the Katz conjecture, the P curvature conjecture is unknown. And now I explain here one fundamental basic property. We attribute to Delaney and Katz. But in the paper of Katz, he attributed to the Delaney. So here's the motivic connections are globally nilpotent. That means this P curvature global nilpotent means that the P curvature is a nilpotent. Okay, this means this is not. This means this one. Okay, this one is a nilpotent. Okay. Global nilpotent just means that it is a generalization of this global vanishing. Okay. Here you have a global nilpotent. It's not necessarily zero, but it's a nilpotent. Okay, this is a nilpotent. So here's a theorem, a deep theorem of Katz. So suppose now you have an algebraic connection over U, and we just assume it is global nilpotent. It actually implies it must have only regular singularity, and all residues are rational. As I recall earlier, that these two properties are really here. This property is a proof first by Delaney using transcendental method, and this is also Steenbrink also involved this topological lattice in this his argument. So this is a transcendental argument. Then now it's pure algebraic, and we just use this as a property. No, it just uses property. Okay. Now we can combine these above two theorems. We obtain, I mean, as I explained, and in this algebraic proof of these two theorems. Okay. So this is a very strong property which deserve, I mean, first thought. Actually, they made a conjecture, so-called just a Gros-Antiquats-André's globally nilpotency conjecture, as I said earlier. So now we go to the second part. I recall some basics of nonlinear Hodge theory in positive characteristic. So all new advance of along the directions based on this. Okay. So here's a Cartier descent. This is a very basic correspondence. So again, K is a character P field, and U is a smooth, and there's a equivalence category. So the first category is a connections over U. Here, I mean, I just use the flat bundle. I mean, this is a notion we used by different geometer. I mean, the flat. But here's nothing to do with the module flat over U. It's just really, I mean, it's a connection with integrability. But in over curve case, it's automatic. I just using the usual terminology. And here, the condition is the vanishing P curvature. And the second category is really just the Wick bundle over U prime. U prime is a Frobenius conjugate of this U. And the equivalence is very, very simple. E is obtained by solving the connection. I mean, E consists of all flat sections of this of the V, and come back is just a Frobenius pullback. And in this case, you have a very tautological connection. I just identify D. This makes sense because for one simple reason. I mean, the D of x power P is 0. P equals 0 implies this, and you can this is meaningful, and this is called a canonic connection. So it's very easy to obtain a connection, a flat connection in character P word. And here comes the advanced version. I mean, this is August Volgotsky correspondence. And fix a W2 lifting of your curve. When here's a curve, I mean, certainly it's liftable. Now you need to make a choice, because this correspondence depends on such a choice. Okay. Then this is a generalization of a Cartier theorem. Now you relax this vanishing P curvature to the nilpotent P curvature, but with this bond. Okay, and here the second category you can allow non-zero Higgs field. So we consider a Wick bundle as a Higgs bundle with a zero Higgs field. So then it's nilpotent. With this zero Higgs field, it's nilpotent. With this condition, then this is again an equivalence category. So and we call in our work we need this from this functor from the second category, from the Higgs category to the connection category. We call it the inverse Cartier transform, and this is a notation C inverse. In our 15-page paper, I mean, we reinterpret this OV correspondence just as exponential twisting of this Cartesian theorem. So their theorem is actually a twisted version of this classical Cartesian descent. And this admits a series of generalizations. I mean, you can generalize to the log pair. I mean, to the logarithm case, and you can generalize to the parabolic case to make it more interesting, to add the parabol weight along the punctures. I mean, something similar like consider Q divisors. I mean, this is we consider rational parabol weight. Anyway, so here's and we can also generalize to the I term as a transversal foliation. I mean this, yeah.
So in that Higgs bundle correspondence for Volgotsky, what was the exponent? The exponent of the
This exponent. this exponent. Oh, you mean the exponent? Just both are p minus 1. Is also exponent of p minus 1. Just means the Higgs field, the theta power p 0. Just yeah. Okay, yeah. Yeah, exponent, okay. Okay. So actually this can be further generalized, so to this transversal foliation. Actually this form encapsulate all above correspondences. That means you can really a very basic elementary differential calculus underline all of this. So this should be known to everyone, I guess. Very simple, and this twisting is very useful. Okay, to extend to make you see the Grundy P curvature case only consider. I mean, it conjectures it's a finite étale trivializable. It means that we consider only families whose phi is just points. And if you want to consider to characterize those family with positive dimension, of course you need to allow the non-zeroness of Higgs field. So such generalization is useful. And now we go to the my theorem. So this is a now. Here is the terminology. I mean, I introduced what is a parabolic bundle. So let me read it. So here's a quadrupole. We have a bundle and have a parabolic structure. Alpha is the index for the parabolic filtration. And this have connections. You do comparable with the filtrations, and you have a filtration, and then you have this filtration on the V, and you restrict this V on every V alpha. And once you have such object, actually you can take a grading of this parabolic bundle respect to filtration to obtain an object in this second category, which is so-called graded parabolic Higgs bundle. I mean, this take grading is like you pass from the Dirac cohomology. I mean, you have the cohomology with Hodge filtration to the double cohomology, which is the direct sum of this HPQ cohomology. So this is a family version of that process. So so this we term as follows. I mean, graded parabolic Higgs bundle is a bundle, parabolic bundle, but here have an important grading structure. Okay, everything should be graded, and you have this Higgs field, which is graded Higgs field. Just mean that you move EI to EI minus 1. Okay, and graded Higgs bundle must be nilpotent. Now here's a key notion. Again, I mean, when talking about Nami Hodge theory in positive characteristic, we need to fix a lifting, W2 lifting. Now it's for the pair, and parabolic Dirac Higgs flow is said to be periodic if there exists an isomorphism of parabolic connections. So for some integer, positive integers. So let's read this. So you start with a parabolic connection, and you choose. I mean, here's data. The field 0 is a data of this flow, which is a satisfy certain. I mean, the level should not be higher than p, so that this graded object is a nilpotent Higgs bundle with exponents less than or equal to p minus 1, so that you can apply the inverse Cartier, which I already explained, and I mean, this dot means actually it's many dots. So otherwise, this will flow away from this screen. So you keep doing this and just repeat this, okay? And it's going down, going up, and down, up. So finally, after F steps, you will get V. You will get VF, nabla F. It's a new connection, parabolic connection. So then, when it says periodic, if you have these isomorphisms, okay?
So in this definition, what does parabolic mean?
Parabolic here, I just to hide the notation. So here actually should write V alpha. Yeah, but I tried this.
By a parabolic vector bundle, do you mean a filtration on the vector bundle?
Yeah, you have a bundle and you have a filtration along at the punctures. Yeah, okay. But you can also, of course, you can basically it's a puncture on the it's a fusion on the punctures. Yeah, and this all operations actually also modify this parabolic structure along this flow. Okay.
So when you say parabolic along the functions, it's just because you work over curves.
Oh no, is this for high dimensional?
But for high dimension,
You can also define.
co-dimension one thing and then parabolic structure like that.
No, you can have a so-called. No, this you have a well-defined notion. I mean, if of a surface, it's fine. I mean, of a close, even over the closing point. You just need to define over all devices, and you have a compatibility at the puncture and the closing point. Fine, it is okay. Yeah, yeah. Why do I feel? Okay, good questions. That's because there's actually important reasons. So first of all, in the geometric situation, parabolic fluctuations encode finer information than this eigenvalues of the eigenvalues. Okay, so eigenvalues must as I said, is a loose of unity. So it's really exponential 2 pi I with a rational number. More than rational number, you have also the position of the this jumping. Okay, and this is, I mean, this actually is important in the. For example, if you don't care about this, then if you ignore this structure, the degree of your logarithm Dirac boundary is negative, and if only when add up this parabolic defect, you get a parabolic degree 0, and degree 0 is very important. Yeah, just for topology reason, I mean, this is very important. So many reasons to explain this.
Does this parabolic structure come from the local monotonic action?
In geometry, yes. Basically coming from the, so you decompose as semi-simple part, and the unipolar part coming from semi-simple part. Say again?
I mean, the local monotony is quasi-nilpotent, so you can consider some power of this guy to get a unipotent.
Right. So as I said, so the information comes from the semi-simple part of this matrix, of this, okay. And here's a lemma. So the initial term of a parabolic down his flow have nilpotent peak curvature. So let's look back this slide. So suppose you have a parabolic connection, okay? Suppose it's periodic. I say this peak curvature must nilpotent. Why? Because this guy is isomorphic to this guy. So the peak curvature of this guy is isomorphic to this guy. But this coming from this guy. This is a graded Higgs bundle. And this must be nilpotent. And the peak curvature of this guy by construction. I mean, I earlier it's computed by Gabor, but actually now it's really become a part of the machinery. So the peak curvature of this guy is really up to, tau is really this guy, is the Higgs field of this guy. So I say it's nilpotent. So it's automatically, you have this nilpotency. So this is a basic fact, but it's important for our understanding. So now here comes up the periodicity of complex numbers. So above I explained the periodicity over character P field. Now we just split out the object over C as Grothendieck did. And here have additional stability coming from you need to fix all liftings and this boundary period. Both are important. Okay, this is like this. I mean, in terms of geometry, is like is independent for any choice of Kerr metric. So it's lifting. As I said, the lifting, the inverse Cartier transform depends on the lifting. Okay. Then here I claim, I mean, respect any lifting, this is a periodic. Okay, this is a strong property shared by motivic connection actually, which is our theorem. So And this bounded period is also, F is also important. We see. Okay. Now, if you say take D is just an empty set, I mean this is a just a periodic connection. I mean you just you can add this D and you ignore this D. So here's also an important remark. If D is irreducible, the filtrations making this reduction, Morphy reduction periodic, actually is unique. So remember, in our definition, we have always a choice of the filtrations. But as I said, if this is irreducible, all filtration is actually is unique determinant. You have no choice. Okay, so this is also this periodicity is very strong actually. So and this is a and this actually the filtration actually also can be abstractly determinant. This is very important. So here's the theorem, main theorem. So you suppose you have a smooth convex curve, then any motivic connections. Actually, U is not important. Actually, the function field of U is important because we define the motivic connections really over the function field of your curve. So any motivic connections are periodic. Okay, but to prove, we just fix a model and a U. Now, as a corollary of this simple lemma, as I explained, motivic connections are globally nilpotent because periodic implies nilpotency at P. Okay, so if there is a periodic in above sense, in this sense, this is automatically periodic, globally nilpotent. So we get this very simple picture. I mean, the global nilpotent is weak than the periodicity, and is weak than motivity. And as explained, by the global nilpotent conjecture, actually these are equal. So actually our conjecture is just these are equal. But we make this conjecture without a priori without knowing this nilpotent conjecture. After we complete our first draft, and then Eno let me inform us that actually this is really conjecture by this nilpotency conjecture. But nevertheless, I mean this I will show that this is an interesting conjecture. I mean before I state my periodic conjecture, let me briefly say about proof. So the nature are quite different. So about this global nilpotency conjecture proof, I mean by the Carr theorem, which as we already mentioned, this is really local computation, and our proof is really a global, and the stability is essential. I mean the stability, make use of stability is essential. But in order to use the stability, you must be first to make commodification of the object. So here, we first step is do the Linz extension. But we need to do a little bit finer to put a parabolic structure on these punctures, not just to get an logarithmic connection, rather a parabolic connection. So that's and we also need to put the Hodge filtration across this puncture. It's really a consequence of the Schmidt Nilpotent orbit theorem. So this is a well known in Hodge theory. This is over C, and again another deep theorem of Simpson. This is polystability. I mean, this really involve the Hermitian-Mills metric. So so associated Cordell-Spencer system to a parabolic Gaussian connection is polystable. It means that it's direct sum of stable objects with the same degree, the same slope. I'm sorry. But actually, in our case, it's all degree 0, so slope are 0. So this is the theorem of Simpson. And this polystability remains after Morphy reduction. So this is a good property. So polystability is a purely algebraic property, but it remains. So it is polystability is an open condition. It means that when you spread out and for p large enough, it all remains polystable, and the number of factors are same. Irreducible factors are same. So the step 3 now is a character P thing. So here you need to generalize the Fontaine-Fardin theorem. Actually, this is a story. I mean, this is Fontaine-Lafayette introduced so-called Fontaine-Lafayette module. But it's maybe unfair to say Fontaine-Lafayette. Maybe Fontaine-Lafayette found this module. It's better. So the Hit theorem is for semi-stable family. This is crucial. I mean, to have the reduced normal crossing fiber. The multiplicity 1 is very important. But in reality, we have the quasi semi-stable family. That means your fiber have a multiplicity, have uncontrolled multiplicity, and you need still have a version of this structure. So here actually the definition of the Fontaine-Lafayette module or the Fontaine-Lafayette module is actually complicated. In the early work of by Lan and Zuokang and myself, we actually reinterpret this Fontaine-Lafayette module in terms of a one periodic flow. And this actually periodic flow is better than this. Actually, even if you formulate that way, this actually generalizes the notion of slightly the notion of the Fontaine-Lafayette module, because you need a stronger lifting property. Here you need to do W2 liftable. So, and I mean, why you have a stronger liftability? Because you have the Hodge theta weight there, and you have a stronger lifting property. And we can do further for the quasi-semi-stable, and it's not one period anymore. It must be periodic. It is inevitable. Actually, I will say that. So we generalize this Fontain's result to the arbitrary quasi-semi-stable, and this is important for us because our connection is only is only defined the function field, and when you do extension, this only you have a quasi-unipotent monodromy instead of a unipotent monodromy. So you have to deal with thing. And this is KXP stuff. And then we have an elementary argument involving the category of the all period object in KXP. So we call the periodicity semi-simplicity lemma. Basically show that if the derived factor of a periodic object is again periodic. And actually this is I believe this actually can be further generalized to a kind of a functoriality between different algebraic groups, push forward and pull back for periodicity. This is true for stability, polystability, or semi-stability. But for periodicity, we can also have some kind of interesting functoriality. Here I just prove one baby version. I can also prove some tensor product version, saying that if you tensor product of two. If you have a tensor product is periodic, then each factor after up to some one-dimensional character is also periodic. So this is also very nice consequence. So, and the last step, last step is restriction back the periodicity over this compactification to the U. So to appreciate this, the difficulty of this theorem is that over U you can do nothing. Over U, you cannot. The point is over U, the things are like this. So it's possible that you have two modules. Two coherent shifts that A direct sum B, which is projective module, but add up is a trivial. Which is just a trivial. Is a direct sum of trivial modules. Okay, so you cannot conclude A is a trivial and B is trivial. It's just projective. But but the naive argument doesn't work. You must compactify and use whole stability and all these things, and add this important information in KXP, and you get this. Okay, so this is quite in just a curve cases, yes, but you can generalize this. Yeah, I just. No, there's nothing about the one-dimensional case. No, it's a. Okay, it's a curve, so it's a puncture. So you can. Here we use, so I mean you have infinite many ways to extend the trivial bundle over the C, I'm sorry. But here we choose a canonical way to extend it, and so that we have the nice property we want. Okay, it's not take arbitrary quantification. So here's really in the first step. Doesn't work? Sorry. It doesn't work. Yeah, I expected that, but the people said this is a new battery, so I charged it, but it's failed again. Yes, I haven't it, but okay. So let us continue. So so now I take one example to explain the periodicity. Okay, to get a feeling about it. But actually, the first example is a rank 1 example, but I want to show some non-trivial example in rank 2. So we have a rank 2 connections. In order to make it interesting, we consider it's regular away from 4 punctures. We assume it is periodic. And by Cut theorem, it is globally nilpotent. And we know that then, we know it is, you have this property, and then you can do the Lin's canonical extension. Now let's assume to assume the connection, the extension have the following type. I just write down the extension. So the bundle will become OP1 and direct sum OP1 minus 1. We call this V. And we have 4 punctures. And the non-trivial parabol, we just assume have one non-trivial parabol structure. That means you have 4 punctures, right? So you literally, you actually have for object extension you have 4. Non-trivial parabol structure, but we just assume have only one non-trivial parabol structure. Okay, we just get a feeling. Now, if in that case, if we say, in infinity, we have a non-trivial parabol structure with a parabol weight 1/2 and multiple 2. So it's corresponding to Q divisor 1/2 times infinity. That's actually this is a Q divisor. Actually, twist this. And then the first bundle, the first copy, OP1, this is have parabol degree 1/2. You need to add this 1/2, and the second bundle have a -1 plus 1/2. It's minus 1/2. Okay, so it's a parabol degree 0. As I said, if you don't have parabol structure, this degree is -1, and there's a compensation coming from parabol structure. And this is stable parabolic bundle. And now we explore further about this periodicity. And so the periodicity over U, and it's actually implied the periodicity over commodification. Actually, this is a big thing. We'll explain this later. And this, okay, actually I explained this, but we'll come back later actually. So let's continue to see the phenomena of periodicity. Now, I said, if it is periodic, it must be periodic with respect to the Harlan-Sigma filtration. This filtration is the only possible filtration to make this periodic. Okay? And then associate grade, and you can take grading. And the associated object will become very simple. So OP1 goes to OP1 minus 1, and tensors is locally different forms. And by degree reason, the left-hand side is 1, and the left side is 1, the right-hand side is 2, because this is -1 plus 3. So it becomes what? You have a 1, 0. Okay, you have a 1, 0. Okay? And this, I label this 0 by Z. And by the right definition of the periodic connection, we will immediately follow that the gradient of this Higgs bundle is periodic. Okay, here I didn't explain what it means for Higgs bundle periodic, but it's really a symmetric to the definition I defined before. Okay, you just upside down the diagram. Here you start with a Higgs term. So it's something like you start with a Higgs term, and you start with Higgs term and flow up and then down and up and down. This you have this isomorphism from the 2 graded Higgs bundles. Okay, so this is really symmetric definition. But actually, it looks symmetric, but actually there's a difference. There's a very interesting difference there. It's asymmetric actually. Sorry, I need to little bit fast. Then actually this Z have a name purely in terms of connection, so-called apparent singularity of this connection. This is defined. This is actually the fact that this apparent singularity, purely in terms of defined in terms of solution of this rank 2 connections, is actually equals to this the zero of the gradient Higgs bundle. Now let me make a small summary. The periodicity of connection imply it have a 4 simple poles by the Carr theorem and 1 apparent singularities. I mean this is we had just 1 singularity. It's just the degree reason. But here's the next result show that apparent singularity cannot be arbitrary. So so here's the theorem. And by with my here's not Lan, it's Lin, and it's my student and my postdoc. And now here's the second proof by Lam and Lit. So here you have this is a conjecture by Sun Yangzuo, and also verified by in the case of family of elliptic curves by Lu Jun, Lu Xin, Yang Jinbang. So remember we have 4 punctures. So we have these 4 punctures, and they will take a double cover of P1, branch these 4 punctures, and now the statement is that apparent singularities appears if you assume the periodicity. Okay, so this must be image of a torsion point of a C on the pi. So that means if Z does not have this property, it is not periodic. If it is periodic, it must be have this torsion property. Okay, and then by our theorem, I said it's motivic objects periodic. That means if this motivic connection, I mean in this case, this must be a torsion. So this is really a strong arithmetic information encoded by periodicity. Okay. Now come the conjecture. So as explained, this conjecture is really a consequence of the nilpotent conjecture. But there's a but. There's a companion conjecture, which is called the periodic Higgs conjecture. So any stable graded periodic Higgs bundle over this curve is motivic. So it looks companion. Okay. By the way, the companion conjecture of this for nilpotent conjecture doesn't make sense. It's wrong. It's trivially wrong. Okay. Only this version makes sense. And it's I shall comment that later that the second conjecture, periodic Higgs conjecture, is stronger than periodic Diam conjecture, and I think it's really a gift of periodicity. Actually, it's hard to prove this, but it's reasonable to prove this, and we will show this actually by a comment. I need to fast. So here's a bit of history. So the periodicity on this Higgs bound is really introduced in 2012 in the unpublished paper. I mean, it's unfortunately it's unpublished. I went to JAG and for 4 years, but they don't get nothing. So it's a very, very stupid thing actually, because new theory, general theory comes and then they recover the results. But this paper contains very important two important ingredients, which is the first is a flow operator. Okay, this is how you define this flow periodicity, and also the lifting of inverse Cartier transformation. Okay, this lifting. So the periodicity can is right the condition to make the inverse Cartier transform of August Voxy to liftable to the truncated ring. Okay, so this is two important ingredients actually. And also, I need to mention that Zhuo Kang also formulate a notion. His arithmetic Higgs bundles is similar to our periodic Higgs bundle here, and also propose a similar conjecture as the periodic Higgs conjecture. Okay, that's a part of history. Now, the periodic Higgs conjecture actually implies periodic Dirac conjecture, and it implies more. I mean, we just to understand, try to prove this in cases, and then we study all uniformizing Higgs bundle over Kaplan-Leibman surface, and we show that it is periodic. I mean, if it is, admits a modular embedding. I mean, this is periodic. If this is in the presence, means that it's the theorem that the conjecture implies the only if part. If it is periodic, it must be admits a modular embedding. And the conjecture is only two examples: Schumacher curve, and so periodicity on the uniformizing Higgs boundary put a very strong condition on that tends to have a modular imputation. And also an example. I mean, this is example. Yeah, studied earlier by me and my postdoc Li Muxi. Okay, so now here's come back to the example I explained above, the rank 2 example, and this periodic Higgs conjecture, I mean, it's not rank. In the rank 2 case, so the rank 1 case is a theorem, but this is a theorem relies on deep theorem by Pink. I will explain. But here's really a big that the periodic Higgs conjecture holds in the special rank 2 case. That means the theorem said that the converse. So as I explained, if this is motif, then the apparent singularity must be a torsion. They prove the converse, which is the implication of the periodic Higgs conjecture that if it is a torsion, the apparent singularity is torsion, then it's motivic. So this is a much deeper theorem. Actually, the method, but depends. I mean, deep. I mean, when you say deep, I mean it really depends on which machinery you use. The machinery used by Yang and Zhu is really is fancy, using long length correspondence and many things. I mean, using a companion, L2 companion, and using a whole series of periodic Higgs flow of truncated ring, and many other things. I mean, many technicality in the proof. And lambda lit is just use instruction, so-called the middle convolution, and then solve the conjecture easily. So he has already guessed the motivic construction underlying behind this thing, so it's easy to get this. Okay, so in the remaining 3 minutes, quickly to say more words. So here is a really, as I said, so this is really the same theme here. I mean, I want to advertise the importance of a non-abelian Pink problem. So Pink have a very fantastic result that a point in complex in a global point of a abelian variety is torsion if only if its more P reduction is a torsion with bounded order. So torsion is any point in the character P is torsion. It's because it's only a finite group, but this bounded order is a big thing. But bounded order is equivalent to bounded period in our case. But I should let you know that the order only makes sense when you have a group structure, but period does not rely on any group structure. So period generalized to a non-abelian case, high rank case. Okay, so we reinterpreted this to get this line bundle case. Periodic if only if it is torsion. Then the non-abelian Pink problem will for a stable bundle of a curve. It is the problem, and actually this also is implied by the periodic Higgs conjecture that if this periodic, it must be finite étale trivializable. So the truth of the problem is really a very special case of periodic Higgs conjecture, but I show you one significance that actually these two conjectures have a same strength. Grothendieck conjecture if only if the non-abelian Pink holds. And you have a better chance to show non-abelian Pink, I guess. You have a more, because you see the quantum P curve really about the function field, the connection of a function field. And what we do is really to make you can have a whole tool of algebraic geometry to study the conjecture using a stable bundle. So this is really significance of the periodicity. So, and these are equivalent. And let me quick. I mean, actually I should stop, but actually there's a deep meaning of the period actually. But I want to show also some interesting fineness problem for friends which interesting on counting points. I mean, this also should be finiteness behind this, and this also meaningless for if you just consider nilpotency, global nilpotency. You don't know how to count. It makes it meaningless to say fineness. But if you in the periodic case, you have a positive integer on the rank, and it must be finite. Okay, so I stop here. Thank you.
Thank you very much. Any questions?
In one slide, we compare three notions. One is multivic, and the second is periodic, and the third one is supposed to be globally nilpotent, right?
Yeah.
But your conjecture says periodic implies multivic. But does is it easier to prove that globally nilpotent imply periodic?
It's not easy.
It's
but
not easy.
In some special case, in the grounded case, this is automatically true.
Okay.
So
I mean, this
so in general
seems to be both algebraic, right?
Yeah, this is a very good question. Yes. So I said, if it is really globally vanishing, then it's okay.
Right.
But it's nilpotent. I need to think more. I believe maybe yes, but here in the periodic involve a filtration. So I still not so easy about this filtration, because you take filtration.
But if you don't have any divisors, then maybe you don't need this filtration. You mean parabolic structure? Or?
No, this filtration is about the Hana-Simon.
Hodge filtration.
Yeah, the Hodge filtration.
Okay.
So I'm still uneasy about this part. But
okay.
I maybe this. But I said if you use global vanishing, is yes.
Yeah.
I see. Yeah, but this is really a.
Okay.
So, yeah.
Actually, about this filtration, sorry. So I'm still, but you. So I want to understand, how does you prove for? Because at the beginning you don't know that they are going to be P of order P, right?
Right.
But then how do you choose it?
So let me explain this way. Maybe this will be better. So actually, so it's a way to understand the Katz theorem. So Katz computation about the P curvature of the Gauss-Meiling connection. So he have a wonderful so-called P curvature formula. He showed that this after the P curvature of a Gauss-Meiling connection is actually a Frobenius twist of the Kodaira-Spencer. Okay, and that's how you get this global nilpotency, because in Kodaira-Spencer is a graded field, and always it's you move the Hodge bundle from the first piece to the last piece, and then finally you go 0.
Right.
Okay.
Right.
Now here, the whole the periodicity actually is a really a nice reformulation. If you just say nice, I won't say maybe deep, but it's really useful a reformulation of this the so-called strict p torsion Fountain findings module structure. So this is really a character p analog of the variation of Hodge structure. So if you explain you the founding module, you can this instill this important ingredient and to put into a more general framework, and then you have more flexibilities.
Thanks. Okay.
Yes, thank you.
More questions?
No more.
Oh, okay. Now we stop here.
Okay.
Let's thank Professor Sun again.
Okay. Thank you.